Welcome back, guys. Now we go for our machine learning review. It's going to be a fast review, but just focusing on the most important subjects, most important points to mention, to discuss with you. To start, what is machine learning for you? And how would you define machine learning? I mean, we talk lots about machine learning nowadays. People have been discussing and trying to apply techniques and applying, of course, many packages. But most of them have no idea what's behind, which are the theoretical questions, answers, and of course, how we can ensure learning occurs. And it's not just by chance. It's not out of the blue. It's not something that's happening without any reason. Basically, when we talk about machine learning, we talk about two main areas, or two main types of learning. There are some gray areas in between, but of course, I'm going to discuss about the two main areas. First of all, we have the supervised learning. The supervised learning defines a scenario where we have data samples and we have input spaces and output spaces. That basically means we have input variables associated to some instance, and then given such input, we must provide some output. So the basic idea is to find or define some classification or regression function in this type of learning to map input to output, to map a given input or instance into an output space. Two relevant papers to discuss that in details, and I really recommend you guys to read those papers and then bring your questions to our virtual office hours, which include basically the paper by Luxburg and Chokov, and also the paper Wolfbert and MacReady. Those two papers are really interesting, really deep in those concepts. Of course, throughout this course, we're going to touch and detail all of those points. But if you guys read those beforehand, things are going to be really easier for you. I recommend. And in the scenario of non-supervised learning, we've got like some results, some theoretical results as well, including this paper by Carson and Emily, which brings into play the stability criteria to prove non-supervised or unsupervised learning. That's really interesting. It discusses lots about topology and how to analyze topological spaces and how that helps us to prove unsupervised learning. I also recommend you guys to read. Besides, that's not the subject of our course. I mean, we are just devoted to supervised learning in this course. But anyway, it's good to have an idea about non-supervised learning. So if you have the chance, please read this last paper too by Carson and Melody. When we talk about supervised learning, we must talk about the bias-variance dilemma. That dilemma comes from statistics. It is really important to define a subspace of functions and how we can, how strong are our guarantees when we talk about supervised learning. So to start with, consider we have like this space where the black dots are just like measurements we collected from a given experiment. Could be any kind of experiment. And then we have two functions which were obtained from this particular sample. First of all, we have this linear function, which is in a solid line, And then we have this dashed function, which is could be like a high order polynomial function. Could be like a degree 5, maybe 6 or 7, whatever. So we have two functions here that were fitted on top of those points, on top of that particular sample. The question that stays here is, which is the best function? Which is the function that I need to choose to represent my sample and to represent new instances or new dots that are going to come later in this graph? So that's the main question. To answer that, we need to assess expected risks. When we talk about expected risks or any kind of expected function, we're talking about the scenario where we're going to have access to every possible point in this scenario, in this particular scenario. So that's the same as having access to an infinite number of black dots happening all over this chart. And then we're going to have access, by having access to those points, we can measure if the linear function is better or this dashed polynomial, high order polynomial function is the best. So that's the question behind the bias variance dilemma. So consider the line, the solid line is the f of x, is our regression function f of x, which obtained like some good results, some good modeling result, but it has some error in our training set. This means it's got like some divergence. As you guys can see here, there is a distance from this black dot to our line, this black dot to our line, to our linear function, linear model, our black dot to our linear function, and so on. That distance, consider that distance as the error. That error should be measured in an orthogonal way, so we should project this black dot here onto the line and measure this distance plus this distance plus this distance and so on to understand what is the total error we have. And consider the polynomial function, this high order polynomial function, passing along all those black dots, so there is no training error. The training error is equals to 0 because we are just lying on those black dots with our high order polynomial function. What's going to be the best? Which is the best? Which is the function to be selected to represent our data? If we consider that G represents an overfitted model, I mean a model that passes on top of those black dots, but if we receive more data here, it's going to miss those black dots that come later. So the question is, maybe this solid black line, which is our f of x, turns out to be better when we receive more unseen black dots here later. This is the question behind the bias variance dilemma. So let's consider we receive more points here, and the solid black line f of x carries on having the same sort of error as it has in my training sample. That's a good sign. That means that my f of x behaves in the same way or in a similar way, let's say, in my sample and on top of unseen examples, of unseen black dots. But what if my polynomial, my high order polynomial function g of x behaves like with error equals 0 in my sample, in my training sample, but when I receive more data here, it misses all of them and it gets really far from those black dots. So the error is going to be really, really high for the high order polynomial function. That basically means my error on a new sample coming later is really far from the error in my training sample. This is the same as saying that g of x overfits. It's an overfitted model on my training sample. So it behaves with zero error in my training sample, but when I receive more samples, it has an amazingly high error. That's a problem related to overfitting. Okay? This is quite interesting. But what happens if we have the opposite? So, for instance, let's say that g of x may be the best function, and points, black dots happening later are going to be really well represented using our high order polynomial function. And they are not going to be that well represented by our linear function. So the question that stays is, how can we select the best function? The best function can only be selected if and only if we assess a new sample, only if we assess unseen data, only if we analyze unseen data and the error turns out to be similar as it is in our training sample. So the scenario we have here is really detailed in statistics under the reference or under the name of bias variance dilemma. That dilemma is central for supervised learning. That's what Vapnik, this Russian guy, used to define supervised learning and used to define learning not just in terms of a sample, but also in terms of expected risks. I mean, when I receive a huge number of unseen data, what's going to happen with the linear and high order polynomial function? Are they going to represent black dots as in the same way they represent in the training sample? Or one of them is going to represent well and the other is going to miss black dots? What's going to be the result? That's the main question here, okay? So this dilemma has two items. The first is the bias, and the second the variance. The bias talks or discusses about the space of admissible functions. The bias defines the space of functions an algorithm uses to select a classification or regression function from. This means if we have like a very restricted bias, so to speak, let's say we're going to select just linear functions, and that bias is only considering linear functions. So we're imposing to ourselves a space of functions that contains only linear modules or linear functions. Of course, if we do that, we're going to reduce the variance. The variance is going to be smaller because we have less possibilities inside that particular bias. On the contrary, if we have like a very relaxed bias considering high order polynomial functions, let's say like fifth order polynomial functions, of course inside the fifth order polynomial space of functions, we are going to have the fourth order, the third order, the second order, and the first order, which is the linear function by itself. This is a scenario where we're going to have a much more complex space of admissible functions. A space of divisible functions and a bias is the same, okay? Just a terminology, just a term that we use sometimes in math, sometimes in statistics, so it changes a little bit, but it turns out to be the same. So if we have like more functions inside that space that our particular algorithm is going to select or to choose from, of course the variance is going to be greater. So we have more possibilities of functions inside that particular bias. We're going to see that just in the next slide, I suppose. Okay, if it's not this, the next is going to be just like a few instances, sorry. So the variance, if we fit like a high order polynomial function over the training data, we can always have a perfect classifier for that particular sample. This is related to variance. So I always have, if my bias is over relaxed, it contains like so many functions that eventually the variance is so huge that independently on the data sample I have, I will always have some data, some classifier that can perfectly fit my training sample. That's a problem, because if it can perfectly fit my training sample, it's going to behave my high order polynomial function in dashed line over here, in a dashed curve, by the way, over here. That's a problem because it brings more complexity to my model. And bringing more complexity, we're going to see later that this also brings a greater chance of fluctuations when new data arrives here in my space. When unseen data happens here, my chance of deviating from those black dots is going to be greater. We're going to see that. Okay. It's the next, as I was expecting. So consider we have this green rectangle here. It's almost like a square. Yeah, I suppose it's a square, containing all possible functions in the universe. So this is the universe of functions. Okay, it's going to be called throughout the course as F all. And inside we have a subspace of functions. This is the subspace of admissible functions F, which we refer to as bias. This is the bias. So the bias is the same as a subspace of functions. Let's say the subspace of functions contains only linear functions. So if it contains only linear functions, I have like much less possibilities here than I would have in this scenario. In this scenario, I have like many more functions. Of course, if I have more functions, I have more possibilities to represent my data sample. What is good on one side, but it is terrible in the sense of convergence. Why? Here, if I start with a given classification function here or regression function here, let's say it is in this place over here, it could converge as the sample size tends to infinity, a training sample size tends to infinity, it could converge to some classification or regression function over here. You can notice that the effort to provide that convergence is it is reduced in terms of the effort necessary to start here, for example, in this space of divisible function, aka bias, start here and converge up to here. As you can see, the bias, when it is really restricted, or let's say our space of divisible function functions is smaller, the variance is smaller. And our effort, our convergence effort, is also smaller. When our bias is relaxed, this is the same as having a large space of admissible functions. Our effort is greater. This is related to the variance, so the variance is greater. What is good about this is that we need less, we're going to see later, of course, but we need less instances, less inputs, less training instances, training examples to provide the convergence here and to find the best possible classification function or regression function in this space of divisible functions, aka bias. In this scenario, it happens differently. We have many more possibilities. We can represent a much more complex scenario, a much more complex data set. However, we're going to need an amazing, huge number of examples to ensure the convergence from this starting model up to a given best possible model inside this space. This is related to the bias and variance dilemma. So the more restricted the bias is, the smaller is the variance. You can measure here the variance. And the less restricted or more relaxed, so to speak, is the bias, the greater is the variance. Of course, the more restricted is the bias, less possibilities we have, and maybe those are not adequate to represent our data sample or our problem. So maybe we need a more relaxed bias. That may happen. That may be the case. And we can only answer that if we assess new unseen examples, new unseen data examples. Okay? So the bias variance dilemma has no silver bullet. Let's say, this is the best as possible space of admissible functions, aka bias for several problems, for all problems, even worse, for all problems. No, that's not possible. That's not possible to say. We cannot say the same for this bias. Actually, we have to assess those biases to say what's going to be the best model. For example, we're going to use a multi-layer perceptron. What is the best number of neurons in the hidden layer to define the bias of our algorithm? For instance, if we have just 2 hidden units or hidden neurons in a multi-layer perceptron, we have some bias or space of admissible function like this. If we have like 10,000 neurons in the hidden layer, we are going to have an over-relaxed bias like this. So the space of admissible functions for the multi-layer perceptron is directly related to the number of neurons we have in the hidden layer. Okay? And now we're going to talk a little about how to assess the quality of a classifier. How can we define that a classifier is better or worse than another? That's really related to the loss function. So first of all, we need to define the loss function. We need to compute the loss function for different classifiers to understand if a given classifier is better or worse than another one. Actually, we're going to see later that we use a lot this loss function to walk on the gradient descent, on the gradient descent method to reduce the training error. Just to give like a quite interesting example, I'm going to open here R. We're going to use this language along our course, throughout our course. And let's suppose I have like some x, could be some variable x over here, that happens to produce values from -5 to 5, and we have like 1000 values. Let's plot this x in terms of x squared. This is similar to what we expect to have for the error. So when I measure the error for a given, let's say here I have several classification functions. Here I have a particular classification function whose error is around 20, as you guys can see here, is around 20, okay? So if that's the error, I should be capable or be able to measure some sort of gradient descent method and understand this gradient to go for a next function, a next classifier, which is, of course, on the left of this one, and then move towards the minimalist possible error. And this minimalist possible error contains the best classifier I can draw from data sample, from a particular data sample. So let's say this is the best possible classification or regression function. Of course, I need some technique, some strategy to go for that best possible classification function. And this considers some loss function. The loss function, as you guys see here, is basically a way of measuring error. It's a way of measuring error in terms of all classifiers, all regression functions we have. And then I need a way of walking towards a minimum. You guys can notice that I expect here to have a convex error function, a convex loss function. If I expect, and I do have a loss function that's convex, this turns out to be easy. But if I have something like this, for example, let's say I have something like this, or even worse, let's try something like this. Let's see, 10 times, no, 10 is too much, maybe, yeah, this is quite interesting. Let's say I have something like this. Here, as you guys can see, I have like some local minimum. But here, if I go to that direction, this is going to reduce even more. It's going to go for smaller values. So this is a region that I have local minimum, but maybe the error equals to 0 happens only here. If I don't have a convex function, and this is the best possible example I can give for you guys at this moment, which is x2 squared, x power to 2 is the best possible convex function I can give for you at this moment. So this is quite a very nice example to have, and a very nice loss function to have. So I can walk towards this minimum, which is a single minimum when the function is convex, okay? And otherwise, I have like some local minimums. Yeah, this is quite interesting. I have like some local minimum here, and then I go to a completely different value, error value over here. Doesn't matter these numbers, okay? Just the shape to understand. Okay, so I should evaluate our classifier in terms of unseen examples. Now I believe you guys can understand that. Of course, I need to compare the errors produced after training and testing our classifiers. So let's recall some important classification algorithms over here. Let's say I have this bunch of classification algorithms here, like perceptron, the multi-layer perceptron, the naive Bayes, decision trees, like C4.5, ID3, or maybe J48, support vector machines. All those supervised learning algorithms are going to build up some boundaries, some classification decision boundaries on top of a space. They are basically going to separate positive from negative instances, positive from negative examples in a given input space. Our idea is we have to measure error here in terms of unseen examples. So we have a sample, we build up some models, some classification model using the perceptron, or using the multi-layer perceptron, or using a naive Bayes instance, or a decision tree, or a support vector machine. Then, by having unseen examples, we are going to apply those models on top of unseen examples and measure the error. Measure what we refer to as the loss function. What we refer to as the error function or loss function. On top of that, we can understand if our model is hitting or missing too much, and of course, if our model is adequate or not. That is how we are going to answer if our model learns something or not. So, observe something. In order to say if our model is learning, we have to define what is learning. What is learning for those algorithms? How is like learning for those algorithms? You have like some basic ideas at this point that we come up with models on top of training data samples, test those models on unseen instances, on unseen data samples, measure error, and then we must come up with the concept of, with this response for learning. Are we indeed learning? Or we're just having like some terrible result, or we cannot prove that we are learning. That's about the statistical learning theory. Can we obtain some sort of formalization to ensure that learning is possible using those algorithms? That's the basics related to supervised machine learning, guys. I hope to see you guys in the next module. Okay? See you.